Want to turn scanned piles and messy receipts into searchable, structured data without guessing which OCR model to use? Imagine a filing cabinet you can search with a keyword. OCR turns pixels into that searchable filing cabinet. It reads printed and handwritten words, extracts table cells, and feeds automation. That simple conversion powers search, analytics, and accessibility. But OCR today is not one trick. It's a toolbox, detectors, recognizers, and reasoning engines. We'll map that toolbox and show which open-source model fits each job, starting with the core pipeline you'll use on real documents. At its heart, OCR is 3 steps: detection, recognition, and post-processing. First, find the text regions on the page. Next, convert those pixels into characters and words. Finally, clean errors and rebuild the structure. Lines, columns, tables. Miss the layout and you'll get words with no meaning. Think of detection as a magnifying glass, recognition as a translator, and post-processing as the editor. Up next, we'll dig into detection, what works and what fails spectacularly. Text detection must handle skewed scans, curved labels, and busy backgrounds. Modern detectors use segmentation and differentiable binarization to outline letters and words. DBNet variants excel at irregular shapes and signboards. If your scans tilt where your receipts curve, the detector decides whether recognition even has a chance. A weak detector turns clean text into garbage. Stick around. Next, we'll look at recognition models that actually turn those boxes into readable words. Recognition converts image crops into sequences of characters. Older systems used handcrafted features. Modern pipelines use CNNs, RNNs, or transformers. Connectionist temporal classification, or CTC, aligns variable length inputs without explicit segmentation. Transformers change the game. Encoder-decoder models can read messy scripts and handwriting when fine-tuned. But even the best recognizer needs clear strokes. Later, I'll show how TrOCR handles handwriting differently than a classic OCR engine. Wait until you see an example. OCR evolution reads like 3 eras. Early OCR used binarization and templates, great for clean print, terrible elsewhere. Deep learning replaced brittle rules with CNNs and RNNs. Transformers then generalized across fonts and scripts. Now vision language models read images and reason about content, not just text. There's also an OCR-free trend, models that generate structured outputs from pixels without separate detection stages. Curious which approach fits your project? I'll unpack the practical trade-offs next. Let's meet the tools you'll actually use. First up, Tesseract. It's mature, CPU-friendly, and supports 100+ languages. It shines on clean, printed pages and bulk digitization, but it struggles with curved text and handwriting unless you over-engineer the pipeline. Think of Tesseract as a reliable workhorse for archives and on-prem privacy projects. Next, I'll show when a lighter GPU library like EasyOCR beats it for prototypes. EasyOCR is a PyTorch library designed for quick prototypes. It bundles detection and recognition for fast results on typical documents. Easy to install, GPU-friendly, and good for multilingual experiments. It's your rapid prototype pick, but it's not built for heavy layout extraction or deep customization. If you need table parsing or production-grade pipelines, you'll need something bigger. Up next, a suite that actually includes table and form extraction out of the box. PaddleOCR. PaddleOCR is a full suite: detection, recognition, table extraction, and multilingual support, with strong Chinese and English performance. It includes layout tools and formula detectors for academic PDFs. The trade-off is complexity and a larger footprint. For invoices, forms, and multilingual academic work, PaddleOCR often wins. But if you want a modular research stack, docTR might be more flexible. Let's explore that next and why modularity matters. docTR is modular and research-friendly. It supports PyTorch and TensorFlow components you can swap, DBNet, CRNN, VITSTR, so you can tailor detectors and recognizers. That flexibility helps when your documents don't fit off-the-shelf pipelines. The catch: you must assemble and test components yourself. It's a developer's toolkit, not a turnkey product. Coming up, TrOCR, the transformer model that shines on handwriting and messy scans. TrOCR uses a vision encoder and a text decoder to read varied scripts and handwriting. It generalizes across typography and tolerates noise after fine-tuning. If you have notes, forms with signatures, or mixed typography, TrOCR often outperforms classic engines. It prefers GPU for speed and benefits from domain-specific fine-tuning. But what if you need reasoning over a document, matching lines to POs or reading charts? That's where vision language models enter the stage. Vision language models like Qwen 2.5 VL and Llama 3.2 Vision don't just extract text. They read layouts, interpret charts, and answer questions about documents. They can find which invoice line matches this PO without stitching multiple tools. The downside is cost and complexity. These models are heavier and require prompt engineering. If your workflow demands reasoning and context, they can drastically reduce glue code. Next, OCR-free models that output JSON directly from images. OCR-free models like Donut and Pix2Struct generate structured output directly from images. No separate detection step, no explicit recognition step, just generate JSON or tables. That reduces error propagation between stages and simplifies pipelines. They work well when you need direct parsing into fields. However, they can be data-hungry and need careful prompt or template design. Want a practical decision rule to pick between these options? I'll give you a clear cheat sheet next. Metrics matter more than model names. Track character error rate and word error rate for recognition. Measure detection precision and recall for text boxes. Test layout retention. Can the model preserve table cells and reading order? Add throughput and cost per page. Robustness on low-res, tilted, or noisy pages is essential. I'll walk you through a simple, repeatable evaluation workflow next, so you avoid surprises in production. Real evaluation. Curate 200 representative pages, annotate key fields, and test 2 to 3 candidate models. Start with defaults. Measure CER/WER, table accuracy and time per page. Add pre- and post-processing, retest, and only then fine-tune the winner. This golden set loop finds practical wins fast. Later, I'll list pre-processing tweaks that often triple accuracy for stubborn pages, so don't skip that step. Pre-processing gives you huge bang for your buck. De-skew scans, denoise backgrounds, normalize DPI to 300 or higher for small fonts, and crop margins. Binarize only when it helps contrast. Super resolution on tiny regions can rescue unreadable text. These steps often beat expensive model swaps. Next up, detection and reading order hacks that stop your tables from collapsing into text soup. Detection hacks. Use strong detectors like DBNet variants for curved or rotated text. For multi-column layouts, preserve reading order by sorting boxes left to right and top to bottom within columns. That simple sorting prevents scrambled paragraphs. For tables, combine OCR with a table detector and post-process cells back into grids. I'll show how regex and domain lexicons tie labels to values in the next section. Language packs, dictionaries, and regex transform raw OCR into actionable data. Enable proper language models for your script. Add domain lexicons, vendor lists, product names to reduce misreads. Use regex to pull dates, totals, tax IDs, and phone numbers. Heuristics can link labels to values on forms. These rules cut false positives dramatically. Coming up, fine-tuning and synthetic data strategies that close the last mile of accuracy. Fine-tuning moves models from good to great. Collect 1,000 to 10,000 samples from your domain and fine-tune recognition for fonts or handwriting. Augment rare cases with synthetic data. Blur, distort, change fonts to teach models edge cases. Fine-tune detectors for your layouts too. These investments pay off in accuracy. But what about cost and deployment? I'll cover quantization and routing to keep VLM bills under control next. Performance and cost tricks, batch pages and cache language models. Quantize where safe and use mixed precision on GPUs. For VLMs, compress visual tokens and limit resolution to critical regions. Route easy pages to lightweight OCR and reserve heavy VLM calls for complex ones. These routing rules cut cloud bills dramatically. We'll touch on security and privacy next, because OCR often runs over sensitive data, and that changes how you deploy. Security first. Redact PII before sending images to cloud APIs. If privacy matters, prefer on-prem open source models. Keep audit logs for processing and store ground truth securely. For regulated industries, an isolated OCR pipeline can be a legal requirement. Next, emerging trends that will shape OCR in the next few years, and why you should care even if you already have a working pipeline. Common pitfalls are predictable. Blurry scans need rescans or super resolution. Wrong reading order needs layout detectors and column tracking. Mixed scripts need multilingual models or VLMs. Handwriting requires TrOCR and fine-tuning. Tables need structure extraction pipelines. Often a fix is pipeline work, not a new model. There's one final practical workflow I recommend for production. You'll want to use it before switching models in anger. Final production workflow. Curate 200 representative pages. Annotate key fields. Test 3 models with defaults. Add pre- and post-processing. Retest and fine-tune the winner. Log costs and latency. Automate routing. Fast OCR for easy pages, VLMs for hard ones. Maintain a golden set to detect regressions. This loop keeps your system stable and economical. Before we wrap, a tiny recap of the most actionable rules of thumb. Recap. Use Tesseract for clean bulk CPU jobs. PaddleOCR for multilingual tables. EasyOCR for fast GPU prototypes. docTR for research. TrOCR for handwriting. And VLMs for reasoning. Add pre-processing, strong detectors, language lexicons, and regex rules. Build a golden set, run bake-offs, and tune only when needed. That concise approach saves time and money. Ready to test a candidate on your own documents? There's one more ask before we finish. If you want a starter checklist, collect 200 pages, label date and total. Test Tesseract, PaddleOCR, and TrOCR, and record CER and table accuracy. Report back with one surprising failure, and I'll help debug. That's the fastest way from confusion to a working pipeline. Now here's a friendly ask to keep these guides coming and to help others find the right OCR path. If this helped, like the video and subscribe for more hands-on AI workflows. Comment with a sample document type you're stuck on, and I'll suggest a focused bake-off plan.